All right. So I have a box here filled with particles, gaseous, picture of gas particles. Let's throw the word gas here. The right side is an area of A, and the length, the other dimension not incorporated yet, is length L with a total volume of V. And I put the serifs at the top of my V for volume to differentiate it from V for speed. So what I want to do here is think about the pressure that the gas exerts on this right-hand side. Well, what causes pressure? I assume people had an intuitive sense of pressure.
Force? Is it force?
Yeah, it's force. Pressure is force divided by area. Let's just go ahead and throw that one up since we haven't officially covered that in the class, I don't think. So pressure is the force per unit area. So at what point is there a force on this right-hand side wall?
When the particles come.
All right, so we want to figure out what is the force that the gas particles will exert on it. And so let's assume that we're just looking at some amount of time delta t. We'll assume that the particles have, in the x component is Vx. This is the, I guess we can set up, that's my x direction right there. Vx is the speed of particles, the x component of speed of particles. I guess officially it's the x component of the velocity, but for right now, let's just assume that all the speeds are the same. Vx is the same for all the particles. We're going to generalize it later. So the only possible particles that could possibly hit it are those that are within this range right here of the Vx delta t. If I'm looking at a certain amount of time, that is the farthest that a particle could travel in that time. So I only care about particles within that part of the box. Because particles are just as likely to be moving right as left, the number of particles that will actually collide are going to be 1/2 of, well, the fraction of particles within this range here, which is, let's see, the fraction of n, so it's the total number of particles times the volume of this part right here divided by the total volume. So this is A Vx delta t over the volume. Again, this is the fraction representing the part of the box that particles could be in order to actually hit the right side. N is the total number of particles, and the 1/2 is because you're just as likely to have particles going left as going right.
So it's A times what, Vx?
Vx times delta t. And I'm going to pretend I can write that more neatly. And it probably helps that I got rid of some of the marks on the board. So if we think about the force that is exerted, I have a particle moving to the right, it hits the wall, it bounces back. We will assume a perfectly elastic collision. So when the particle hits the right and bounces back, it's going to be traveling with some speed Vx to the right, and then it's going to bounce back with some speed Vx to the left. Bring in some of the stuff we have done within the past month or so. Impulse. What does impulse equal?
Force times change of time.
All right. And no real harm assuming the same force on all of them. What else does impulse equal?
change in moment.
So I have these particles of some mass m traveling, let's go ahead, to the left and then to the right. The change in momentum is going to be, well, the momentum afterwards minus the momentum beforehand, momentum final minus momentum initial. Since I'm only really caring about x direction right now, again, we'll generalize it later, this just ends up being 2 mvx. I guess that's the magnitude of that. In essence, I have mv minus negative mv, which is force divided by time. So the force that is exerted becomes 2 mvx over delta t. That's for one particle. But if we actually wanted to look at the total force that is acting on it, so that's for one particle. The total force, well, we have that many collisions actually happening, so it's that times this. So I have 1/2 times n, a vx delta t over the total volume, times 2 mvx over delta t. So this is for the n number of particles that are colliding, n called particles. Well, we can't get rid of some stuff here. Stunning visual effects like black on black. All right, there we go. Delta t goes away. The 2 and the 1/2 go away. So I'm left with number of particles times the area times the mass of the particle times Vx squared over the volume. That would be the total force. Or the total force. Since pressure is force divided by area, it's the force per unit area, well, let's divide both sides by area here, and so now I have the pressure is equal to that force divided by area, which becomes the number of particles, mvx squared over the volume. Now the average speed, we'll start working our generalizations here. The average speed squared is just actually going to be the square of each of the components added together, vx squared plus vy squared plus vz squared. Because we have a velocity with 3 components to it, and to get the magnitude, you do the 3-dimensional Pythagorean theorem. We can write this average v squared here. This is just a separate notation for average. It's the average vx squared plus the average vy squared plus the average vz squared. So although we originally were looking at Vx, but recognize that Vx here is only part of the total speed, and there's no reason to think that any one of these is greater than another. If we do have just random motion in there, the average Vx value should be equal to the average Vy value, which should be equal to the average Vz value squared. Actually, third squared in there. So these three things on average, statistically speaking, should be the same. And so this is equal to 3 times the average Vx squared. So we can take our bit right here and we can generalize it slightly, because originally I said to assume Vx is the same for all the particles, but really this is just an average value. So we will transform this to the pressure. I'm going to go ahead and multiply both sides by the volume, just get rid of my fractions, is equal to N m average Vx squared, which is N m times 1/3 of the average speed squared. If we do take the concession that all the masses are the same, I can bring the mass inside here without any loss. And so I have N times 1/3 of mv squared. Well, it's a lot. This looks very familiar. What is mv squared? Or where have we seen it before?
Kinetic energy.
And what is the formula for kinetic energy?
1/2 mv squared.
Nice. But I'm missing the half here, so let's go ahead and throw the 1/2 in there. So we got N times, if I throw a 1/2 in out there, I have to throw a 2 on the outside. So this is equal to the number of particles times, we'll put the 2/3 up front as tradition dictates, times this average kinetic energy. Questions to hear? I'm trusting that there's at least several of you in here who've had chemistry before. What is the ideal gas law?
PV over T.
PV equals
over T.
so pressure times volume is equal to the number of
Moles.
number of moles times the Rydberg constant, I believe, times the temperature. If only we had some value for PV. So based upon our model there, this should be equal to 2/3 times the number of particles times the average kinetic energy. So we basically have a constant here, R is a constant. N is the number of moles, which should bring happy memories to those people who've taken chemistry. What is a mole anyway?
Say a certain number of particles.
Do you remember what that number is?
6.022 times 10 to the negative, or times 10 to the 23rd?
Yeah, 23rd. You took it one more decimal place than I could have. 6.02 times 10 to the 23rd is what I remember. And then I guess 2.
Yeah.
Okay.
If I
All right.
remember correctly.
Just like a dozen is 12, a score is 20. A mole is a really huge number. So we can actually change this around slightly. Instead of the number of moles times Rydberg's constant, I'm still feeling confident with Rydberg. Is it?
I think so.
I'm trying to think of the other R's. It's not Rayleigh.
No, it's not.
Austin's about to reveal it. The important thing is it's a constant that we're going to get rid of in just a second. All right, so we're going to go with that, and if the chemistry people say it's something different, then just remember they're wrong. So this number of moles times the Rydberg constant is actually equal to the number of particles times a different constant. That's a lowercase kb. This is known as Boltzmann's constant. I know it's going to shock you, but it was named after Boltzmann. T is equal to 2/3 N delta times the average kinetic energy. And so we now have a relationship here. The capital N goes away, or officially gets canceled out. So the average kinetic energy of particles in a box is equal to 3/2 times this constant times temperature in Kelvin. So we have a direct relationship here between temperature and kinetic energy. Did you?
Yeah, it's not the Rydberg constant, they just refer to it as the ideal gas constant. Rydberg constant is something like 1.0 something.
Okay. All right, I apologize for the misinformation. I don't suppose I wrote it down, that'd be crazy. No, I just left it as a capital R. So when you start talking about temperature or change in temperature, what you're really talking about is a change in kinetic energy. So if I have a box here, a separate box, I have some material which has some temperature to start with. What I'm claiming is that it has a certain amount of energy to start with. So potential and kinetic. I put energy into it, so we'll call this energy in. I'm going to call this E sub 0 for sort of the original amount of energy we have. Energy can come out. I'm going to have to write it. In and out. Then the final amount of energy I have in here is, well, I start with a certain amount. I add energy in. I take energy out. It's nothing particularly spectacular there. Let's just do a quick example to make sure I don't have a sign in the wrong spot. So we start out with, let's say, 10 joules of energy. I put 5 joules in. 3 joules come out, and so I should have 12 joules left over in the box. You find more?
Yeah, Regnald's constant.
Of course, old Regnall. I apologize to its entire lineage for having forgotten it. And so this should be energy in, our original energy 10 plus 5 minus 3, which is 12. All right, so it works out. Now, this right here, not earth-shattering, but we can make it look a lot more complicated. And that's what we call thermodynamics. How do you get energy out of a system? Well, you get energy out of a system by working. That system does work, it's losing energy. So instead of calling this energy out, we're going to call this work. It's work done by the system. Instead of this energy in, since we're dealing with temperature here, we're going to call this heat. So we'll use the letter Q, because what other letter would you use for heat but the letter Q? I assume it stands for quantity of something. So our final amount of energy is equal to the initial amount of energy equals the initial amount of energy plus Q minus W. But we can make it even more complicated. Let's throw in people. What were they thinking? Because sometimes thermodynamics people don't want to look at the box as the system, but the environment as the system. And so this energy into the box is actually energy being lost by the environment. This work is not work being done by the box, but it's being work done on the environment. And which means that my signs might change for the exact same concept. The first part of thermodynamics textbooks is explaining which one they are doing. And God help those who have textbooks which use two different conventions. This whole concept here of you start out with energy, you put stuff in, take stuff out, you end up with the final amount. They decided to make this even fancier, and they call this the first law of thermodynamics. Now, there's a first law, so of course, there's a zeroth law, because they came up with it afterwards, and they didn't want to rename them. The zeroth law, I will just pose to you the question of, if I have a glass thermometer, so just picture classic thermometer with, I always picture mercury, but they don't use mercury anymore, or let's just pretend it's mercury. I have a mercury thermometer sitting here on the wall. Of what is it measuring the temperature? Of what? What temperature is it measuring? If I have a thermometer on the wall, it's measuring the temperature of something. What?
Temperature?
Pardon?
Room temperature?
It is not.
The temperature of the mercury in the thermometer.
Yes, that's what's being measured. So the thermo people came up with this idea of, we can pretend it's equal to the temperature of the room, but we have to make an assumption here. Who remembers the transitive property of equality? This is not just some random thought, it is connected. From math class, transitive property of equality. I guess it's not taught anymore? Or does it sound familiar to anyone? Sort of, okay. Were you homeschooled?
Yes.
Okay. It was a stab in the dark there. I was trying to think, if it's not being taught for everyone, I'm assuming it's not a regular part of the school curriculum anymore. All right. Transitive property of equality is an earth-shattering concept. Here it is. If A equals B and B equals C, then
C equals it.
A
Or A
equals-
equals C.
I know, your whole world just changed at that moment. Except we're going to make it sound fancier because it's thermodynamics. If system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. That's the zeroth law of thermodynamics, right there. Thermal equilibrium means that statistically there is no energy exchange. It could happen on the microscopic level, but overall, if you look at the average, thermodynamics is huge into statistics. If you look at on average, the temperature is not changing because the temperature is averaged the same. Kinetic energy is the same, so if particles bump into each other, there's really no on average exchange of kinetic energy. Zeroth law of thermodynamics. Second law, that's the depressing one. The one that if you think about long enough, you'll go, what's the point of any of this? I mean, as in existence. Second law. Nature tends towards disorder. Or you can also write it as entropy increases. In other words, if we did absolutely nothing, if we never came back to this room, came back, went into a time machine, came back in a million years, things would be falling apart. It takes effort in order to put things in order, even though it might not look like there's an order here, but there is some order. If I actually had to straighten out the room, it's going to cost energy to do that. It will not naturally tend towards order. Things will not naturally just show up in the right cabinet. From an energy point of view, I have two particles cruising along. If one particle has higher energy than the other one, they collide. The one that has the less energy should probably gain energy. The one with the more energy will lose it because it's transferred. What we're saying here is that ultimately all energy is going to go to the same in the end. Everything with the same energy. In other words, you can no longer get energy from any objects, and therefore, at that point, no work can ever be done. There is an incredible video put out, I think it's by someone who goes by Melody Sheep, which looks at the rest of the time for the universe. That really illustrates this really nicely. Another way of expressing the second law is you can never break even. Energy-wise. If I am going to lift a book up to a certain point, I've given the book potential energy. The amount of energy it takes me to do that is going to be more than the potential energy of the box. You will not break even. Perpetual motion is impossible because you will always lose energy. Even if you come up with a system that works temporarily, in the end, it all goes to this. Entropy increases, everything's the same, it's just one giant soup of particles. And then, Isaac Asimov has a story about this, and basically, there's a reset button that has to happen. And then the third law is that you can never reach absolute zero. Zero Kelvin. You can get close. I mean, they're down to picokelvin, but zero will never happen. Unless there's some statistical fluke, but that's only temporary. All right, so on that cheery note, this is the last face-to-face until hopefully next semester. But I hope you have a very safe holiday. Don't forget the semester is not over today. Some of you still owe me stuff. And yeah, I guess that's it. It just really seems odd. But then again, it has since March.
If we found one day that there was enough mass, that there is much more mass, and that the universe will recontract, no?
Right?
Then that wouldn't go against the second law.
I've wondered that. I have not asked someone who has studied it more than I have. I think that what they would claim is that the way the particles would come back would be in a random order, and so you miss out on, it's not like they're going to come back to the same order that they started in. They will come back to some randomness. And I'm not quite sure how to justify it, but I have had the same question. I don't have an answer for it.